In the previous subsection, we developed the perturbative solutions for the state amplitudes order by order. We saw that instead of solving the full time-dependent Schrödinger equation directly, we expand the wave function in the basis of unperturbed stationary states and then solve for the time-dependent coefficients a sub n of t. By expanding those coefficients in powers of the perturbation parameter, we obtained the zeroth order, first order, and even second order amplitude equations. Now we move to the next key question. What is the physical meaning of those amplitudes? That is the focus of this subsection. Here we will interpret the perturbative amplitudes in terms of transitions between quantum states. In particular, when a system is initially prepared in one unperturbed eigenstate and then subjected to a weak time-dependent perturbation, the perturbation can gradually generate non-zero amplitudes for other unperturbed eigenstates. Physically, that means the system can make transitions from the initial state to other allowed states. So the first important quantity is the transition amplitude. This tells us at the amplitude level how strongly a particularly final state is populated by the perturbation. But in quantum mechanics, what we actually measure is not the amplitude itself, but the corresponding probability. Therefore, once we obtain the transition amplitude, we square its magnitude to obtain the transition probability. So this subsection provides the direct link between the mathematical formalism of time-dependent perturbation theory and a physically measurable prediction. Conceptually, the flow is very simple. The time-dependent perturbation couples the initial state to other states. That coupling produces transition amplitudes, and those amplitudes determine the transition probabilities. This is one of the most important parts of the chapter because it is where the theory begins to speak directly to experiment. Once transition probabilities are known, we can predict how likely it is for a particle or quantum system to move from one state to another under the action of a time-dependent perturbation. And this subsection also prepares us for the next major step. Once we understand the general expression for transition probability, we will be ready to apply it to the especially important case of a time harmonic perturbation, where resonance behavior naturally emerges and ultimately leads to Fermi's golden rule. So in summary, the previous subsection derived the amplitude corrections mathematically. This subsection gives those amplitudes their physical meaning by connecting them to quantum state transitions and observable transition probabilities. As mentioned in the previous slide, for many applications, the main physical quantity of interest is the transition probability, and to lowest non-vanishing order, that probability is already obtained from the first order solution. So now we apply the first order amplitude equation to the most important practical special case to better understand the transition probability under a time-dependent perturbation. Let's consider a quantum mechanical system with a particle initially occupying only one single state, say the ith state, before a time-dependent perturbation is turned on at time t equals 0. In this case, the initial state is represented by a single unperturbed stationary solution as shown. This means that the zeroth order amplitudes can be written by this equation. So only the ith zeroth order amplitude is equal to 1, and all the others are 0. Here we also impose the natural initial condition for the higher order corrections at t equals 0 by setting all the correction terms to the expansion coefficients to 0, as shown in this formula. This means that at the instant t equals 0, before the perturbation has had time to produce any correction, the system is still entirely in the original unperturbed state. Then we substitute the initial condition into the first-order differential equation. Again, since n runs over all indices, a sub n naught equals 1 only when n equals I, otherwise it vanishes. So the sum over n collapses immediately and we obtain the result as shown. This is a major simplification. Instead of a sum over all initial amplitudes, only one survives, namely the one corresponding to the initially occupied ith state. Then by integrating the right-hand side from 0 to t and applying the initial condition as shown, we obtain the final result given by this equation. This is one of the most important formulas in first-order time-dependent perturbation theory. It gives the first-order amplitude for finding the system in state M at time t, assuming the system started in state I at t equals 0. The perturbation matrix element H sub mi prime of t tells us how strongly the perturbation couples the initial state I to state M. The phase factor e to the I omega sub mit reflects the energy difference between those two unperturbed states, and the time integral accumulates the effect of the perturbation over the interval from 0 to t. This formula is the direct route to transition amplitudes and very soon to transition probabilities. Now let's substitute the first order amplitudes back into the wave function. The full state wave function is written as shown here. To first order, using the initial condition that the system started in state I, we write a sub n of t as shown, which is approximated by delta sub mi plus the perturbation parameter times the first order correction term. Substituting this into the expansion gives the result as shown. This expression shows the physical picture very clearly. At time t equals 0, the first order correction vanishes because of the initial condition. So initially, the system is exactly in its original unperturbed state I. That is an important consistency check. For times t larger than 0, however, the perturbation can generate non-zero amplitudes for other states n. In other words, the system can evolve from the initially occupied state into other unperturbed eigenstates. Now we point out an extremely important selection rule statement. If h sub mi prime of t equals 0, then the amplitude for state n remains 0 at first order. In that case, the perturbation does not connect the initial state I to state n, so the transition is forbidden at this order. By contrast, if h sub ni prime of t is not equal to 0, then the perturbation does couple the two states and the transition is allowed, at least in principle. This is the origin of the selection rules we often discuss in quantum mechanics and spectroscopy. Whether a transition is allowed or forbidden is determined by whether the corresponding perturbation matrix element vanishes. So the key message on this slide is not just the formal wave function expression. The deeper message is this. The perturbation redistributes amplitude among unperturbed states only when the relevant coupling matrix elements are non-zero. We now arrive at the quantity that is usually of greatest physical interest, the transition probabilities. Suppose the system starts in state I, and we ask for the probability that at time t, it is found in another unperturbed state F. That transition probability is given by this equation, where A sub f of t is expressed as the expansion in powers of lambda. We see that the transition probability is the absolute square of the projection of the full state wave function psi of t onto the normalized unperturbed state phi sub f naught, assuming psi of t is also normalized. In other words, it is the absolute square of the overlap between the full state psi of t and the unperturbed final state phi sub f naught. So the probability of finding the system in the unperturbed final state f at time t is given by the absolute square of the corresponding expansion coefficient A sub f of t. Now, since the system was initially in state I, and if the final state f is different from the initial state I, then the zeroth order coefficient of state f must be 0. So the leading non-zero contribution to the transition probability comes from the first order amplitude, as shown. Finally, setting lambda equals 1, we obtain this formula for the transition probability. This is the standard first order transition probability formula. We see that it depends on the time integral of the perturbation matrix element between the initial state I and the final state F, multiplied by the oscillatory phase factor determined by the unperturbed energy difference. So the transitions are strongest when the time dependence of the perturbation matches the natural Bohr frequency between the two states. That resonance idea will become even more important in the next part of the chapter, when harmonic perturbations and Fermi's golden rule are introduced. Please also note that the full wave function remains normalized, as mentioned earlier. So the appearance of non-zero probability in a previously unoccupied state means that probability amplitude has been transferred there from the initially occupied state.